In this video, we're going to take a look at a pressurized water reactor, also called a PWR. We'll take a look at a PWR nuclear power station. I'll show you all of the main components and I'll show you how it works. So here is our nuclear power station. Got a bit of saVRee branding on it, as you can see. There are two blocks, one on the right and one on the left. In the power generation industry, you might classify the one on the left as block A and the one on the right as block B. This just means that we've got two separate sources for power generation. If we spin round to this angle, we've got our nuclear island, which is everything within this box here. And then we've got our conventional island, which is everything within this box shown now. We call them conventional islands and nuclear islands because the one side of the plant is conventional in the sense that it belongs to a thermal power station. For example, if we had a coal-fired power station, everything within this building would be in both the coal-fired power station and our nuclear power station. Let me just take a cross-section for a moment. Everything within this building includes the steam turbines, the steam condenser, which is under here, and then over here we've got an electrical transformer, that is this item here. So all of that makes up our conventional island because we could literally just take all of these parts and use them in a coal-fired power station, a gas-fired power station, or any other type of thermal power station. To the right though, we've got our nuclear island, and what we've actually done is we've changed our heat source. Instead of using the chemical energy from coal or gas, what we're going to do is use the energy from a nuclear fission reaction. We're going to harness the heat from that reaction and we're going to use it to boil water and create steam. So just to complete the understanding here, we're essentially sending steam over to our steam turbines, and we're doing that from the nuclear island from our pressurized water reactor. If we were looking at a different type of thermal power station, we would most likely see a water tube boiler which forms our heat source. Let's have a look at some of the parts that make up a PWR power station. We've got this dome-shaped building. This is our containment building. If we have radioactive leaks, we want all of the radiation, all of the radioactive material to stay within this dome, within this sealed space. You can see the border where my mouse is going along now, and all the way up here. The containment building is constructed of steel reinforced concrete. It's going to be about 1 to 1.5 meters thick, let's say 3 to 5 feet thick, and it is gas tight. So any leakage within the containment building is going to be contained within the containment building. This is great because one of the big worries with nuclear power is simply that some of that radiation, some of the radioactive material might leak out, damage the environment and be hazardous also to humans, animals, wildlife, and pretty much every other type of organic life. So we don't want that, and hence we have a containment building. Let's quickly run through the parts and then we'll go through them in a bit more detail, and I'll explain to you exactly what's radioactive and what isn't. At the heart of our PWR power plant is a nuclear reactor. That's the item at the center of the screen. Around the nuclear reactor, we have steam generators. It's these cream items over here. There's actually 4 of them. 2 are shown here, and you can see 2 on the other side. The green items are reactor coolant pumps, and the red item, or reddy pink, is a pressurizer. We can see the connections through the piping. We've actually got some ones on the top of our steam generators. They go off to the steam turbine. Let's have a quick look through the process now that we know the name of the parts. We've got the nuclear reactor, within which we have a core where our nuclear reaction takes place. It's a fission reaction, which means atoms are split. The opposite of this would be a fusion reaction where atoms are combined. This reaction generates heat. We have a primary coolant that's circulated through our reactor and our steam generators. If we go from our reactor coolant pump here, the primary coolant travels along here into the reactor, it's heated up, and then It's going to come out along here into our steam generator, and then it travels up the steam generator, up to the top here, and then it travels back down again, down through this connection, along here, and to our reactor coolant pump. That's what's termed a loop. We've got 4 of those loops. This makes this particular PWR a 4-loop type reactor. See, we've got the exact same setup on this side over here, and the same setup where our 2 pumps are in the back. So primary coolant is circulated through the pump, through the reactor, to the steam generator, and then back to our reactor coolant pump, also known as an RCP. We term this section here the cold leg. It's the cold leg because the primary coolant is cold. It's heated up in the reactor, it comes out and enters the hot leg, enters the steam generator, gives up its heat, and then comes out and enters the cold leg. So the steam and water has absorbed some of the heat from the primary coolant, and that's why we have a hot leg and a cold leg, due to the temperature difference between the two. Temperature difference is also referred to as delta T. Pressure difference, delta P. Within the steam generator, we've got secondary coolant. What's going to happen is we're going to pump feed water in through this connection here. It's then going to travel down within our steam generator, travel back up, be heated, turn to steam, come out of this connection here, and go to the steam turbine. So here are the connections coming out, the 4 connections from the 4 steam generators. Really speaking, you might only have one single connection. It depends if they connect on a common manifold. Steam is delivered to our steam turbine. That's this item here. The high pressure end is over here, and the low pressure end is actually within these 3 boxes. You can see here, those are low pressure turbines. The steam passes through the turbine, it passes across some blades, causes the steam turbine rotor to rotate. That causes a rotor within the generator to rotate. Here is our generator. We induce electrical current in the generator stator, and then we're going to generate electricity or electrical power, which we send off to a transformer and then distribute through an open air switchyard usually and into the electrical grid. So the entire steam turbine setup is exactly the same as what we would see in a normal thermal power station. Hence, this is the conventional part, the conventional island of our PWR nuclear power plant. If you don't know how steam turbines work, steam condensers, etc., we've got videos on all of those topics, so make sure you check those out. I'm going to assume you've got a little bit of knowledge concerning this area of the plant, so that we can focus more on the nuclear side in this video. Before we leave the conventional island though, notice that there are 4 pipes coming back. That's these 4 here. Those 4 pipes are bringing feed water to our PWR. So we're sending steam to the steam turbines here. The steam passes through steam turbines. We give up some of that heat, which causes the steam turbine rotors to rotate. Then we pass the steam through a condenser. It condenses to water, and we pump the water back through these 4 connections here to our PWR, specifically to our steam generators. Let's go back to our PWR for a moment. We've talked about the reactor, we've talked about the reactor coolant pumps and the steam generators. There's only one other item of interest here, although arguably the whole thing is of interest, and that is the pressurizer. We have a pressurized water reactor, and it's the pressurizer that gives it its name. What we're actually doing is pressurizing our primary cooling circuit. If we come down here, you can see that the pressurizer connects to the hot leg, that is our outlet from the reactor to the steam generator, and we use the pressurizer to maintain the primary coolant circuit at a relatively high pressure, somewhere around 150-160 bar. Why are we doing that? We're doing it because we want the primary cooling circuit, or the primary coolant, to remain in a liquid state at all times. We don't want the primary coolant to boil. Some localized boiling may occur, but we don't want it to boil and change state from water to steam. Boiling water reactors work like that, but PWRs do not. What we're using as a primary coolant is light water. PWRs are light water reactor power plants, and so are BWRs, boiling water reactor power plants. Light water is water that's been deionized and demineralized. So essentially it's similar to the water that you would get out of your tap at home, but it's been deionized and demineralized. The main goal being that we want the water to be clean. We want it to have low suspended solids, or total suspended solids TSS, and low dissolved solids TDS. Light water reactors and PWRs are the most common type of nuclear power plant that you will see. The other main type being a heavy water nuclear reactor, which is less common. So we've got the pressurizer, which is maintaining the primary coolant under pressure. It's preventing the primary coolant turning to steam. When we pass the coolant through the steam generator, it's going to give up some of that heat to the secondary cooling circuit, the secondary coolant. Let's have a look at all of these parts now in a little bit more detail, because it's a bit easier then to explain what each of them does. Here is our nuclear reactor. The core is located in the center of the reactor. You can actually see we've got some fuel bundles. That's these items over here. These are full of enriched uranium. We manufacture the enriched uranium in pellets. We put the pellets into rods, and then we assemble the rods into fuel bundles, which we can change about every 18 months, roughly, when the fuel is spent. Water enters into the reactor through this connection here. This connection would be our cold leg from the reactor coolant pump. The water travels down. You can see this is the downcomer part of the reactor. Travels down here, around the base. It's going to be heated as it then travels upwards across the fuel bundles. You can see some inlets. Go over to here, the center of the screen now. So the water travels to the base of the reactor. It then begins to travel upwards. It's going to be heated. The temperature increases. And then we pass the heated primary coolant out through this connection here. It then enters our hot leg. Then it would go towards our steam generator. Here's our steam generator. Here's the hot leg. So we've got the heated primary coolant coming along here, going into the base of our steam generator. Then it's going to travel upwards. So let's go up to the top here. It's going to loop around. You can see that the heat exchanger has this loop shape, this sort of bowed shape. This is a U-bend. So it's going to come up, around, and then down. It's going to be within the tubes, and then pass out through the cold leg. So the primary coolant is flowing through these tubes. The design of the steam generator is essentially a massive heat exchanger. They might be up to about 20 meters in height, and they weigh a lot. Think 700, 800 tons. The primary coolant flows up through hundreds of pipes around here and then back down again. And surrounding these pipes, actually tubes is what we should be calling them, surrounding these tubes is secondary coolant. If we look over here, we've got the feed water coming in. It flows downwards. Down here, this is a downcomer. And then it's going to flow in here, surround our tube bundle. It's going to be heated by the tubes. And then the heated secondary coolant moves upwards, not only due to natural convection, because as it's heated, it's actually less dense and will tend to move upwards anyway, but also because it's forced through by a pump. As the secondary coolant is heated, some of it turns to steam. The steam then flows up through these tubes here, and we begin to clean the steam. We've got primary separators and secondary separators, or primary and secondary cleaning stages. Here is a primary stage, and here is a secondary stage. And the goal with both of these stages is to dry the steam, remove moisture, remove the water, so that we get dry, clean steam with a very low moisture content going to our steam turbines. We don't want to send water or have any water carryover to our steam turbines, because if we do that, we'll damage the steam turbines. So the secondary coolant, which is steam, is sent to the steam turbines. Let's leave the secondary coolant, because we know the steam goes to the steam turbines, it drives the steam turbine, that drives the generator, and we generate electricity, etc. And then it's returned through the feed water connection. Let's follow our primary coolant a little bit further, and we can go and have a look at the reactor coolant pump. Here is our reactor coolant pump, RCP. It's probably one of the largest types of pump that you're ever likely to see. The impeller itself looks very similar to a Francis turbine, if you've ever seen one of those. The fluid, in this case liquid, is drawn into the center of the impeller. Let's just put that into motion. It's drawn into the center of the impeller, and then we're going to throw or discharge the fluid outwards, and this is what we term a mixed flow impeller, because we actually draw the fluid in through the middle upwards, and then we discharge it outwards radially. And because of this one direction at the bottom and another direction out to the side, we classify the impeller as a mixed flow impeller. The idea with the impeller and the pump in general is to increase the pressure of the fluid, our primary coolant pressure, so that we can then send it back, you can see the discharge arrow here, to our nuclear reactor. So suction on the bottom and discharge on the side. Drawn in from the steam generator on the bottom and sent to the nuclear reactor on the side. We've got a sealing arrangement and loads of other parts here. We've also got a large motor top here and a large flywheel. So that's our reactor coolant pump. It's like a normal pump but incredibly big, even having its own heat exchanger to cool it down. The only item that we need to have a look at now is the pressurizer. Here's our pressurizer. At the base of the pressurizer we have a heat source. These are electrically heated rods. We're going to heat the primary coolant and turn some of it to steam. You can see that the pressurizer is partly full of water. The top part of the pressurizer will be full of steam. We have a cold water inlet. This is actually from our primary coolant cold leg, where we spray the cooler water, the colder water, into the top of the pressurizer. And we do this because we want some of the steam to condense and turn back into water. We call that changing state or changing phase. When the steam condenses, the pressure in the system reduces. When we heat more of the primary coolant and it turns to steam, the pressure in the system increases. This is because steam has a much larger volume than water, a ratio of about 1800 to 1. So the more steam we have up here, the larger the pressure is going to be within our primary coolant circuit. So the pressurizer allows us to regulate by either heating the primary coolant water or cooling the primary coolant steam, the pressure within the primary coolant circuit. We're doing this simply because we want always that the primary circuit remains in a liquid state. By regulating the amount of steam at the top of the pressurizer, we can achieve this in quite a simple way, really. What's interesting about the pressurizer, though, is it does have multiple other functions. It allows us to remove non-condensable gases such as oxygen and CO2, and functions in a similar manner to a deaerator, because when we remove these gases, we reduce the likelihood of corrosion within the system. It also functions as a safety device. We measure the water level within our pressurizer, and we mount the pressurizer itself at a higher level than our steam generators and all other parts of the PWR. We do this because if the water level should decrease, we're going to get an alarm before the coolant level drops below a critical height and we damage some of our power plant parts. For example, we don't want the primary coolant dropping so low that the reactor core is no longer surrounded by coolant. Primary coolant is a coolant, it cools the reactor core. It also acts as a moderator to control the fission reaction within the reactor. It's essential that the reactor remains full with primary coolant to prevent damage to all of the internal parts of the reactor. The steam generators also should be full of primary coolant so that we don't get any tube ruptures or uneven thermal loading across our tube bundles. So the pressurizer has multiple functions. It's not there just to pressurize the primary coolant loop. I hope you now understand exactly how a pressurized water reactor works, all of the main parts that make up a PWR power plant, and how they work together to generate electricity. If you want to use any of the 3D models shown in this video, then head on over to saVRee.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at saVRee.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.